Thank you for the introduction. And I need to come to more of these because I learn a lot of things. Just in the introductions, I realized how old I am. Ed Oliver and I were in the Air Force together at the weapons lab at Kirtland Air Force Base back right after I graduated from AFIT in '81. So, and then that struck me that I had a few jokes I might mention, and especially seeing the gong in the back of the room. But then I quickly realized that any jokes I have are going to go over everybody's head here because I can see how the age group of the group I'm about to speak to. Although there's a few in the back with ties on that I think would pick up on some of those jokes. But if I say something humorous as we go through this, feel free to snicker. That way I'll know you're awake. Otherwise, please allow me to welcome you to DC. What a great time to be here. Just know the weather is hot, but it's a wet hot. So, and so if halfway through this I take the jacket off, you'll understand. But truly, we want to welcome you here. This is what a great opportunity for you to see some of your colleagues in this program, to look and learn about the areas of science that they find fascinating. You get a chance to talk to folks that could mentor you through your careers. You get to talk to folks, program managers at headquarters. Most of us, the guys standing around with ties on. You'll get to talk to people from the labs, scientists and engineers that really would like to take advantage of some of your talents. So do talk to them. There's lots of opportunities here today. Please take advantage of those today and through Saturday, I guess. Barb mentioned earlier that recently the department has signed a formal agreement that Office of Science and the National Nuclear Security Administration would work together towards exascale. That's, we've worked together in the past, but this is really a groundbreaking opportunity in that we are going to take the dear resources we have and work together towards something that's going to be important for science in the future. Because we signed that, you guys get the benefit of only one welcoming speech. I mean, traditionally, both of us got to get up here and say welcome. So we cut that short today. You get one welcoming speech. Of course, it's me you get to hear, but you just have to live with that. What I wanted to start out by saying is I'm the luckiest geek in the world with a tie. And I say that in a serious way because as you hear the message I think I have to tell you as we go through this, I want to tell you why I think I'm that lucky. Years ago I got to diddle with bits as I progressed to being in the military. You kind of get out of that technical part and you get up into the management, and then you never get a chance to do the fun stuff again. So you have to find ways to do fun things, and I think I found it. So let me take you back a bit to something that an experience I had that I think can have application to what you'll be going through as you go through your career. Way back when I first joined the Air Force, one of my short-term goals was to have the Air Force send me to get a master's degree and pay me a captain's pay to go to school. And I had these visions of grandeur going back to my debauched days on campus and having all kinds of fun. The Air Force selected me to go to school, and they sent me to Wright-Patterson Air Force Base to the Air Force Institute of Technology. And of course, my visions of long hair and cut-off shorts and all was vanished in a second. But it's the best thing that ever happened to me. And it's the best thing because at that institute, they had quite a few resources that most universities don't have that allowed you to have the kind of instruments and resources to do things that were fun to do. They required a thesis, a 12-hour thesis, which I wasn't sure I really wanted to do as we started this. But as I got into it and found out the kind of resources they gave me to work on problems that had some significance to the Air Force, it became a lot of fun. In fact, it became a labor of love. And as I left the Institute, the one thing I carried away from me was, if you want to do something that's personally rewarding, find a place that can get you the resources so that you have the opportunity to make the advances you personally want to do in your own life. So that was the lesson I carried away. And I don't want to talk about that. I mean, the kind of things I got to play with were, in those days, called electrically erasable, programmable, read-only memories. And bubble memories. Has anyone ever heard of a bubble memory? Okay. So we were getting samples from the factory, and I was trying to make them work, and they wouldn't work as I wanted them to. I was under the pressure of a deadline of a thesis, and all that great opportunities they presented taught me a lot. In the end, I was successful, and that's why I carry away the lesson that if you really want to have fun, you really want to feel rewarded in your career, find places to work where you get the resources you need to get your job done. A lot of places are constrained, and that seems like such an obvious lesson. I'm sure you're probably going to sit there and go, well, duh, Bob. I mean, everybody knows that. But I guess I want to repeat it because that's what you get when you come to DOE. And so some of this is a bit of a sales pitch to say you have the opportunity here to talk to people, but you ought to really take it a serious thought about what a DOE can provide you so that you can provide advances for the betterment of the nation, as it turns out. So all this kind of sounds like Nirvana. You know, well, let me take a step back. Believe it or not, if you come to work at DOE today, you still have the opportunity to get in on the ground floor of supercomputing. If you think back just 6 years ago, the ASCII program had the goal of getting a 100 teraflop computer, bringing it to fruition and letting it and having it as a tool for science. The main goal of that machine was to prove that you could do science at that kind of scale, that this would actually do something productive for the nation. It turns out that a year after that came into production, we started hearing scientists and engineers talk about computing being the third leg of science. To me, that's what a great accomplishment for DOE, to bring computing to that scale. You still hear about that today. In fact, we've gone from the day of proving that would work to a day when now we talk about predictive capability. In those days, we couldn't even talk about that. Today, we talk about using these large machines to predict with confidence problems that are of interest to us, scientific problems. So that all makes it sound like, darn, we're pretty far down the road, and this is like we're on the threshold of Nirvana. All we got to do is plug things in and get answers, and you'll be able to advance your science kind of at the snap of a finger. But I might have forgot to mention that the science is really hard. We don't know what predictive capability really means, and we're about to slam into a wall that'll change the way you do computing. Other than those things, we're probably okay. So let me talk just a bit about the predictive capability. So I said, if you look at predictive capability, we've become pretty good at validating the physics that go into our codes. We've known how to do that for a while. I know at least in the NNSA side of this, and I know in the science side of this, the way we build the codes are tied very closely to the experiments that are done, and we know pretty well how to validate things. What we don't know so well is how to quantify the uncertainties that we have in the answers. In fact, we know we need to make advances there, and the Office of Science has programs in their math area focused specifically on uncertainty quantification, that they have grants and vehicles with the labs and academia to kind of advance that science. We in the NNSA have what we call the Predictive Science Academic Alliances program, which is totally at universities. So both of us recognize there's a problem there. Both of us are working together to fund activities that will advance that science. We would encourage you, as you go through your fellowships and all, to figure out, if you do figure out how to do uncertainty quantification in your problems. First of all, we encourage you to do it. You need to do it if you're going to be credible. Second of all, please provide the lessons back to us. And in the end, I would say, if simulation is going to continue to be the third leg of science, that we have to, it's incumbent on us to conquer the uncertainty quantification part of this, and because we have to know how good our answers are. Otherwise, in the future, we'll find that nobody cares. With respect to the ever-evolving world of computing technology, I would say if you look back, or if you look at where we're even at today, gone are the days when frequency advances will help you solve your problems faster. Gone are the days when CPUs connected to, or individual CPUs are connected to multi-gigabytes of memory. You can have memory-rich environments. And gone are the days when low core counts and a few attached processors, GPUs to your cores, make it fun a fun world to do computing. Those days are gone, but and to be replaced in the future by a future dominated by what I'll call seemingly infinite amount of flops, manifest in extreme levels of parallelism, but constrained by access to memory. If you think for a second, we've come through an era where we were doing science sequentially. We got vector processors that allowed us to accelerate some things a bit. We went into a parallel era that I just mentioned, and we thought that that was extreme parallelism in those days. We ain't seen nothing yet. And this is the genesis a bit of the exascale initiative that you'll hear Bill talk about a bit in the future. I'm just here to tell you that when we hit that wall, things are going to change. You can look at that as a glass half full or half empty. You can look at it and say, oh no, everything's going to change, woe is me, because it's going to happen. Or you can look at it as an opportunity to get in front of your peers, conquer the complexity that's going to come upon us, and make advances in your area of science that put you in front of all your peers. You can do that. We can help you do that. For example, let me just ask you to consider one thing. This is a comparison. In the good old days when we first started the ASCII program, we bought our first teraflop computer. It was the ASCII Red machine. It came in, it broke the teraflop barrier, and we upgraded it to 3 teraflops in the late 90s. If you look at that machine, it was a machine that would fill this room plus a little extra, 2,500 square feet. It sucked up a half a megawatt of power. You could do 4,500 way parallelism with it. In those days, if you were a hero programmer, you could step up and take that challenge and build parallel codes at that scale. If you look at what's going to happen a decade in the future, you're going to see a single chip. It's going to be 10 teraflops. It's going to have about the size of a dime. It's going to suck up about 200 watts. Compared to that big room I just told you, 3 times the flops. The problem is, well, it also is going to have order 10 CPUs, maybe 100 GPUs. Each core on the chip is going to have, well, it's going to have probably 1,000 GPUs, and each core is going to have like 100-way threading. So if you add that up, that's like 100,000 way parallelism compared to 4,500. It's an order of magnitude greater parallelism. It's going to be a challenge, but an order of magnitude is no big deal for the people in this room. I know that. But then I probably forgot to tell you that we need 100,000 of those actually to build an exaflop machine. If you want to build something for science at exascale, it's now going to take, what, 5 or 6 orders of magnitude. Now you got a problem that I think you can get your teeth into and make you feel good about getting a solution. But then I forgot to tell you that actually the chip itself will have constrained access to memory that I mentioned earlier. So the memory is going to be an order of magnitude less than you saw on that red machine, and it's going to take 100 times longer to get a bit from memory to the machine itself. So now you're going to be extremely constrained. And oh, by the way, if you can build a machine that big, when we build a machine that big, we will have to worry about resiliency. What happens? Can you actually get an answer in a period of time before the machine dies? And you're going to have to worry about programming models because things are going to change. will be forced to change. So those are the kind of things you're going to have to deal with in the future if you want to be a leader in your area of science. So I mentioned the computer science and all that, and I said I forgot science is going to be really hard too, but you know, we have great faith in you because to get into this program, it was highly competitive. We know you know the science. So we take that as a given. Now, from my perspective, being a computer geek, we just got a lot of big problems to overcome in the computer realm, and we'd like for you to be there to help us get through that. The challenges that, such as those I presented, with those challenges come opportunities. We'd like for you to come to our labs and help overcome those challenges and capitalize on the opportunities. The opportunities you'll have to do your science at a scale that puts you as a leader in your area of science. You know, I can see the trends. I mentioned a bunch of those to you, but what I don't know is how this whole thing is going to shake out. What I do know is that those that step up to the challenge will have an advantage over their peers, and those that conquer the complexity will be the leaders in their areas of science. As you spend the next couple of days discussing your pioneering work, please do take the time to talk to your sponsors. Again, those are mostly people with ties, but in this heat, maybe we'll shed them a little later. Take those opportunities and ask them what brought them to work at DOE. I'm going to bet you that they're going to tell you it was the opportunity to do something for their country, to work in an area that challenged them mentally, and that was very rewarding to them in the end. If that isn't what you hear, then talk to me later and I'll buy you your favorite libation somewhere. And you don't even have to buy me one if I'm right, okay? One way. So I hope you've sensed by now why I really love my job. It's because I'm working with world leaders that are making a difference. And most people don't get that opportunity. I got the opportunity, I took it. I hope many of you will do the same thing. Come to work at DOE, get the resources you need to pursue your passion and help make a difference for the nation. Some of you probably won't want to do that, and that's fine. We all, I just want to say it's been a privilege, and we will consider it a privilege to have worked with you as you go through this fellowship and as you choose other places to go. That's fine. We were just privileged to have some time and help you build your career. With that, I ask if I may have gone too long, so there might not be a chance for questions. But I can tell you Bill can answer all the questions. We are joined and with a common vision, so